name's Ted Merrill, and I'm here to talk to you a little bit about a brand new biosolids processing facility that we've just opened up in Pasco County, Florida. This is a one-of-a-kind facility where we're producing a Class AA fertilizer out of the biosolids product that is produced at 4 of the wastewater plants here in Pasco County, along with other municipalities contributing as well. The process that we looked at when we designed this particular facility is that we wanted to accomplish several goals. One of those goals being we wanted to produce a Class A product without doing any bulking. And by bulking, I mean we didn't want to add any particular products to the biosolids in order to produce the Class A material. So that ruled out a few technologies right off the bat. The other piece that we wanted is we wanted to have that volume reduction. We wanted to start out with more product than we finished with, because that ultimately would mean less transportation costs or less effort put into the final destination of that particular material. So what we did is we started to focus on the different Class A technologies that we knew that existed and we'd worked with throughout municipalities all across the United States. One of the technologies that we really liked was harnessing the natural energy of the sun. And so we looked really hard at the greenhouse technology. To produce a Class A biosolids just using greenhouse technology, you would have to dry the biosolids to 90% solids. That can be done, and it is done in different parts of the world through greenhouse drying. However, it's very inefficient from a time perspective. So we knew that would push the envelope of an efficiency level to just do it in greenhouse drying. Another piece of technology that we really liked for its simplicity was oven drying or belt drying. Belt dryers are used all over the world as well, and they're designed to take biosolids from an as-received moisture level and dry the material to 90% solids as well. So receiving a product of biosolids from 15 to 20%, whether it's off of a belt press or a centrifuge, and then drying that material to a 90%, again, would take a very large amount of energy, natural gas, methane, whatever the energy source might be, and it would be very efficient from a time perspective because you'd have to move the product through the belt dryer very, very slowly in order to get it that dry. So then we backed up and said, let's look at the 503 regulations and what of the regulations sticks out to us as something that we could maybe wrap our minds around. The one particular method that we really liked, which was a PFRP for pasteurization. PFRP is the process to further reduce pathogens. Pasteurization, the definition, according to the 503 regulations, was 30 minutes at 70 degrees C. What we liked about that was it was very definitive. 30 minutes, 70 degrees C. That we could wrap our mind around. So we said, all right, using greenhouse drying and using belt dryers, how could we come up with a unique way to combine those technologies to produce that product? And so here's what we did. We started out with the greenhouses and we said, all right, the greenhouses are effective at removing moisture when conditions are controlled. And so we looked at how do we make greenhouses where we can control it as much as we possibly can. So to do that, we fully enclosed the greenhouses, and then we put ceiling fans inside the greenhouses that we use to stir the air inside them. Each of our greenhouse units, we call them pods, is about 1.25 acres apiece, so about 65,000 square feet. In those greenhouses, we have 21 large fans that are in there. They're stirring about 3.5 million cubic feet of air all the time, and that's enhancing the evaporation effect of the biosolids. Also in those, we have activated carbon systems that are doing two purposes. Number one, they're removing the odor and cleaning that up to as high a level as we possibly can before it's discharged. Number two is they're helping us to remove the moisture. In order to remove the moisture, we needed more air capacity than we did to remove the odors. And so we worked with a company to design the activated carbon systems to be able to pull 200,000 CFMs of air through the greenhouse units. We control that air by louvers on one end of the greenhouses. Those fans then pull the air through the greenhouse and exchange it out the other end. In order to make the greenhouses safe for being able to work in them from a labor standpoint, we needed to have 6 exchange rates per hour to meet the NFPA 820 code. We have 12, so we were exchanging it 12 times an hour, so every 5 minutes we are exchanging the air in the greenhouse units. Another particular part of our design that we wanted to improve upon was to make sure that we had receiving stations that would allow the trucks to come in, dump the material, drop it without having issues with it getting on the equipment, on the tires. And so we designed 2 receiving buildings that we have where we elevate the truck and trailer. The trailer would be totally encompassed with the building so that it can unload the material all under roof. And then we also have a catwalking mechanism where the operators could go up and help break free any particular biosolids that might still be sticking to the insides of the trailer. As we dry the material in the greenhouses, we lay it across the floor, and then we agitate that material with a tractor and a tillage tool called a Fulk. That Fulk unit is actually designed to just stir the material, taking the dry crusted biosolids that's on the surface, rolling it under and putting and exposing the wetter moisture material that's underneath. We'll stir that biosolids 3 to 4 times a day, and as it's drying, we're actually reducing the volume in the greenhouses. So by the time the material gets to 60% solids in the greenhouses, which happens to be our target dryness, we've reduced the volume down to about 33% of what we've actually started with. That material then we scoop up, we put it on the Serpentex conveyor systems. Those Serpentex conveyors take the material and they bring it into our process building. We wanted to increase the timeline and efficiency of that operation, so we've actually reduced the travel distance for the payloaders by having transportation buggies that actually receive the material so the payloader can get right back to work and get another scoop. That material comes into the unit that's way behind me, the big stainless steel unit, which we call the day hopper. The day hopper is where we store each day's worth of product so that we can process through the pasteurizer out of it as the process goes on throughout the day. That day hopper holds about 3 semi-loads of material, even though we may only be producing about a load and a half. So out of the day hopper, then it goes on to another Serpentex conveyor, which is the conveyor that you see that winds around and goes all the way up on top, and it drops the material into the belt dryer that's been slightly modified. The top chamber of the belt dryer is actually what we call our heat up chamber. That heat up chamber is where we're actually placing the biosolids 2 to 3 inches thick on the belt and forcing hot air up through the material. As we do that, it becomes a fluid bed. That biosolids air is being blown through at a rate of 30,000 CFMs, so it is actually making the biosolids dance on that belt as the air is penetrating up through it. That also gives us the assurance that the biosolids is all evenly being heated, because we're simply trying to preheat that biosolids material to bring it up to pasteurization temperature in a single pass operation. As it's doing that, we're going from ambient temperature to 70 degrees C or 158 degrees Fahrenheit on our heat up chamber on the top belt. As it reaches the end of its travel on the top belt, we have the luxury of having 2 ways to control that belt. We can leave it set so that it just meets temperature before it gets to the end. If it meets temperature way back at the 50-yard line, we can speed the belt speed up so that we can increase the throughput capacity. As it gets to the other end, it drops out into the lower chamber, which we call our pasteurization chamber. That pasteurization chamber has a very similar belt design, a very similar air design. However, the belt speed on that chamber never moves any faster than 30 minutes from start to finish. That's how we can document one of the 2 aspects of the definition for pasteurization, which is 30 minutes at 70 degrees C. By having the belt never move any faster than 30 minutes, we meet that qualification in the method. The second qualification then is 70 degrees C or 158. That is monitored through thermocouples located throughout the pasteurization chamber so that we can monitor that temperature to assure that we always keep a constant temperature above that level for the entire process. As the process gets to the other end of the pasteurization chamber, it drops out onto another conveyor that was manufactured by Serpentex, goes over into the load-out building where we have a load-out design where we can load a semi-trailer without having to move it, or we can bulk store the material for later distribution. The material is registered under the label of FloridaGreen. It's a 740 fertilizer, and we are marketing that through composting, we market it through fertilizer manufacturers, through sod growers, market it through sod, hay, grass, sugar cane, and orange groves. And so that's some of the markets that are out there and available. And so we're really excited about it, and we're sure glad you're able to join us today to hear about it. Thank you.